You ask an AI a question. A fraction of a second later, words appear as if the answer came from nowhere. But it did not come from nowhere. It traveled through cables, processors, cooling systems, transformers, and power stations before returning to the screen in your hand. For years, we have asked how intelligent AI can become. Now we need to ask something more physical. Can the electric grid keep feeding it? This is TrendSpark, where we follow the signal behind tomorrow's technology. Electricity demand is already accelerating. The International Energy Agency expects global consumption to grow by 3.6% in 2026 and another 3.8% in 2027. AI is not the only reason. Air conditioning, electric vehicles, factories, and broader electrification all matter. But data centers are becoming one of the fastest-growing new loads. They consumed an estimated 415 terawatt-hours worldwide in 2024. By 2030, the IEA projects roughly 945 terawatt-hours, slightly more electricity than Japan consumes today. That would still be less than 3% of global electricity use. So this is not an energy apocalypse. The problem becomes more serious when that demand is concentrated in a handful of locations. A hyperscale AI campus does not behave like a new office building. It can require power on the scale of a factory, sometimes several factories, operating every hour of every day. In the United States, data centers used approximately 4.4% of the country's electricity in 2023. The Department of Energy estimated that this could rise to between 6.7 and 12% by 2028. Unlike millions of small devices spread across a country, these facilities often arrive in clusters. One town may suddenly need new substations, transmission lines, and generating capacity because several enormous computing campuses chose the same region. AI training can also create synchronized swings in electricity demand. Thousands of processors begin and finish operations together, producing patterns the grid must measure and manage. A data center can be designed and opened in 2 or 3 years. A major transmission line, power station, or nuclear reactor can take much longer. The computers improve on an 18-month rhythm. The infrastructure powering them may be planned in decades. When demand arrives before the grid is ready, somebody must decide what gets built, where it goes, and who pays for it.
So the cloud is a warehouse full of hot computers attached to a power plant. Who named this thing? And the bigger question, when it needs a larger grid, who pays?
The processors are only part of the system. Electricity is also needed for networking, storage, backup systems, and cooling. According to the IEA, cooling can represent around 7% of consumption in an efficient hyperscale facility, but more than 30% in less efficient enterprise data centers. Water use is even harder to summarize. It changes with the climate, cooling design, local electricity supply, hardware efficiency, and time of day. A Lawrence Berkeley study found that the water used by individual computing workloads can vary by more than 10,000-fold. So whenever someone offers one universal number for the water used by an AI prompt, be suspicious. The honest answer is, it depends enormously on where and how the computation happens. The cheapest unit of electricity is the one you never need to generate. More efficient chips, smaller specialized models, better software, and smarter cooling can deliver more intelligence from every watt. Liquid cooling is increasingly replacing rows of power-hungry fans. Workloads can also be scheduled more carefully. A training job that is not urgent might run when renewable electricity is abundant, or move to another region where the grid has available capacity. Not every task can wait. Real-time services still need immediate answers. But AI facilities do not have to behave like permanently inflexible loads. Efficiency alone will not erase the growth. New electricity supply is also needed. Solar and wind can be deployed relatively quickly, while batteries can move some of that energy into periods when it is needed most. Geothermal could provide continuous power in suitable locations. Natural gas offers dependable generation, but creates additional emissions and fuel dependence. Nuclear power offers firm, low-carbon electricity, but new reactors remain expensive and slow to approve and construct. There is no single magic source. The likely answer is a combination of generation, storage, transmission, efficiency, and flexible demand. The scale of the challenge is already changing corporate energy strategy. Google has signed an agreement with Kairos Power intended to unlock as much as 500 megawatts from multiple advanced nuclear reactors, with the first deployment planned around 2030. Microsoft entered a 20-year power agreement supporting the proposed restart of 3 Mile Island Unit 1, now renamed the Crane Clean Energy Center, providing approximately 835 megawatts to the grid. Meta has announced agreements involving existing and future reactors representing as much as 6.6 gigawatts. These are major commitments, but an agreement is not the same as an operating power station. Many projects still face construction, financing, regulatory, and technical uncertainty. Energy is only one part of the contract between a data center and its neighbors. Communities may gain construction work, permanent jobs, and tax revenue. They may also face new transmission lines, land use, water demand, backup generators, or higher infrastructure costs. The most responsible approach is not to hide those trade-offs behind the word cloud. Companies should disclose expected electricity and water use, fund the infrastructure their projects require, and demonstrate that ordinary customers will not carry an unfair share of the cost. Where possible, data centers should become partners to the grid, using batteries, on-site generation, and flexible computing to reduce demand during critical periods. The grid should not merely serve AI. AI infrastructure should also learn how to serve the grid. AI is not literally running out of electricity, but its growth is colliding with an energy system that moves more slowly than software. The winners of the next AI race may not simply be the companies with the largest models or the most processors. They may be the ones that produce the most useful intelligence per watt and earn the trust of the communities powering it. The future of artificial intelligence will not be built in the cloud. It will be built on the grid beneath it. TrendSpark is learning too. Did the evidence make this story clearer? Was Spark's interruption useful, or should the fox stay away from the electrical equipment? Tell us what worked, what we should improve, and what you want us to investigate next. Nuclear power for AI, liquid-cooled computers, or AI managing the electric grid. We will read your comments before we build the next episode.